Hi, this is Suman, and the topic that we are going to look at is resource scheduling for project management scenarios. This is done as part of the assignment component for Artificial Intelligence Applications and Foundation course for the autumn semester. And this is a two-member group of Chhavi Chaudhary and myself, Suman De. So we will be looking at resource scheduling, how it is done, its implications with graph coloring, its representation, and we'll also look at a way of how to solving it in case of conflict management. So in this video, we covered the problem statement. We also look at why this is used as an AI concept and how the same can be modeled around the concepts available. We'll look at the solution. We'll have an explanation of what we are doing and a basic code walkthrough of how to find minimal colors required to color a complete graph with a particular use case. The problem statement talks about resource scheduling as a project and asset management scenario and how it is dependent on multiple individuals or resources associated with a project. Now, in different organizations or industries, we see that there are ample number of human resources associated with a particular project or a task, and they might be, doing different tasks at the same time. So this forms a major challenge when it results into a conflict between two tasks, and one has to go for a waiting stage as one particular resource is associated with a different task. So we realize the same with graph theory and core topics, and we use core topics of constraint satisfaction scheduling under the applications of artificial intelligence further in this presentation to first represent and also solve the same. In this assignment, we work towards realizing these problem statements through graphs. A vertex coloring of an undirected graph G with V vertex and E edges is a labeling of the vertices such that no edge in E has two endpoints with the same label. Now, what we are really trying to solve here is a corresponding optimization problem so that there are less number of conflicts in a particular project. Now, vertex coloring decision problem is intractable, and usage for graph coloring are some of the important usage of graph coloring are where we have a limited amount of resources, as we'll be looking for this particular topic. Also using register allocation problem, and also in various other areas like data mining, clustering, networking, image capturing, etc. In the selected problem statement, we try to find answers of a well-laid project plan. So let's say there are multiple projects which are available, and with that, there are multiple tasks associated for a particular project. Now, in different tasks associated with the project, we can see that multiple resources might be associated to multiple tasks, resulting into conflicts, and as a result, waiting time for execution of a particular task. In this particular topic, we basically form the groundwork of usage of concepts like scheduling, constant satisfaction problem, and planning. Now let's take an example of this particular scenario where we have 7 projects and or let's say 7 tasks in a particular project. Let's consider this to be tasks, and each task has been named as A, B, C, D, E, F, and G, and each of the tasks is currently owned by a particular team. So task A is done by dev 1, dev 2, tester 1, and technical lead 1. B is done by dev 3, tester 2, tester 3, and technical lead 2. At the same time, the others are also done by their own respective resources. Now we see that for one example, like technical lead 3 is the TL3 or the technical lead 3 is part of task D, task E, and task F, resulting into a conflict between all of them. So when TL3 is busy with C, there is a possibility that D, E, and F tasks are pending or are in waiting state. So there's a conflict which arises, hence resulting as a major problem for the resource scheduling scenario. So can we represent the scenario that we saw in graph? Yes, we can. So each task here is nothing but a node or a vertex. So A, B, C, D, E, F, and E, F, and G are nothing but each of the tasks, and an edge between them represents a common resource between them or a conflict. So if we see A and D, there is supposed to be one resource which is common between them. So if you look at A and D, we see that um, tester 1 is a tester for task A as well as task D, and as a result there is an edge between them. And as we saw that for C, D, E, and F, there is technically three who's common, so there are edges between all of them, and hence this particular graph was formed. So we'll later look into what is graph coloring in depth, but if we decide to color the graphs in a manner where adjacent graphs are not having the same color, so this is how it should look. So this graph was colored using four colors: red, saffron, green, and pink, where we know that two adjacent nodes won't have the same colors for indicating the same. And this particular thing means that for there are four different tasks working in parallel, and when one is in progress, the other three might be in waiting state, which forms as a major conflict for any project. So the same project can be denoted in this particular way as well, where we have removed dependency of D with C and F and E, making this two color problem, or a graph, colored graph which has chromatic number as 2. Now next, the importance of this particular paper is to look at how we can have lesser number of chromatic numbers, hence lesser number of waiting time. So here we quickly look at a code which helps us find the number of colors in a particular minimum number of colors required to color a graph. So we'll quickly jump into that particular point. Here we have written a small C++ code which basically calculates for the same scenario that we have mentioned. So we have seven nodes and 8 edges, and we have denoted each of the edges available there in that particular graph, and we try to see how many minimum number of colors we require to color the graph, hence the waiting time. So the waiting time will always be the number of minimum colors we are getting minus 1, because one particular color will represent the task which is currently being done by a resource, whereas the other two are pending. So if we run this particular code, it will give us a minimum color, and in this case it shows that the given graph that we were seeing in the particular presentation can be colored with minimal 3 number of colors. So going back to our presentation, if you look at this particular graph here, this can be colored with 3 colors instead of 4, which is represented, and maybe if we remove the number of edges, it can go up to 2. So next we move on to resource constraint scheduling, and how do we tend to solve further this problem once we have the number of colors, but how do we reassign edges so that the number of conflict is lesser, which will be now explained by Chhavi for the later part of this presentation. Thank you. Over to you, Chhavi.
Now, hello, this is Chhavi and I am going to discuss how to find the minimum number of colors to color a graph. The minimum number of colors which is required to color the graph is known as the chromatic number of a graph. We are going to discuss the problem of how to solve the resource constraint scheduling. This deals with the scenario that how to schedule the tasks or jobs which are associated with the start time, a deadline time, and also the penalty associated to delays. Now, how to solve the graph the resource constraint scheduling problem, we are having the optimal approach like integer linear programming, or we can also apply the search technique to find the solution like depth first branch and bound or best first branch and bound. We can also apply the heuristic solution of finding the independent set. The graph coloring problem statement is this, that we have to assign the vertices colors such that no two vertices which are directly connected sharing an edge have the same color. We have to assign the different colors to those vertices which are directly connected. The graph coloring problem are NP complete problems. This is an example of colored graph which are having some conflicts among them. So the chromatic number of this graph is 4 because we have used 4 different colors to assign this graph. There are various applications of graph coloring here. We are showing the air traffic flow management. We have aircraft scheduling also, register allocation applications. In communication networks, we are using the graph coloring statements, and we are having different approaches to solve the scheduling problems using the vertex coloring. The nodes are scheduled as a jobs, and the edges are denoting the conflicting pairs of the jobs. In the graph coloring, we are modeled the scheduling problems for the vertices and the edges. Now the approaches which we have used for graph coloring in our assignment are the optimization based solution and the decision based solution approach. In the optimization, we have to minimize our objective function. That is, we want to minimize the number of colors to be used to color the graph, and decision based solution for coloring the graph. So we are going to find the independent set. The independent set contains those vertices which are not connected directly. So they can be colored with the same color, because in our independent set it is guaranteed that no two vertices in the same set have the same color. So we find the independent set, and the maximal independent set is that in which the addition of any new vertex to the set violates the condition for independence. We have the feasible coloring solution at the end of finding the independent set, in which our objective of satisfying all the constraints we got in the independent set by applying the heuristic solution. Thank you. That's all from my side.